Okay, good evening everyone. Welcome to the warm desert of Eastern California. My name is Mike Jerry, and we're going to do some astronomy tonight. Tonight specifically we're going to do the September Cloudy Nights EA Observers Challenge. We've done many of those in the past, and Say has got a very nice list for us this month. He's actually, let me turn this off, and so you can actually see my webpage. But he's actually got a really nice stellar evolution challenge list where we're going to see things from the nebulae that form stars all the way through the young stars and older stars and what happens to them as they die. And as we work our way through, things will get older and older. And so that's going to be it's a neat theme, and so it's a really cool way to do some astronomy, because you kind of learn things as you go along. And we're going to be doing that tonight. And so we're going to start off with some nebulae and things like that. But before I get to that, what I should do is show you my setup. And that's going to be here. Let's get it started. It's being very slow. Okay, so here is my setup. And it opened two of them for some reason. I'm using an 8-inch Schmidt-Cassegrain telescope, riding on an AM5 mount. And let me kill this so I don't... Okay, and so it's all riding on an AM5, ZWO AM5 harmonic mount. And I'm sitting at a table behind here, bringing this all to you. And tonight, I'm not using the Hyperstar, which is shown on here. Tonight, I'm actually using a 3.3 reducer on the back of the scope. I got one on the used market. They rarely show up, but I found a Japan-made 3.3 reducer for my C8. So tonight I'm operating at right about focal ratio of f4.2, and so we're going to be about 850 or so millimeters, which should be nice for the smaller objects. And so that's what I'm using tonight to see our various objects. And so for the medium and small stuff, it's going to be really nice. For the very large stuff, it's not going to work so well. Like the very first thing, North American, is going to be way too big for my view. So we might actually just skip that. Just do Pac-Man and Wizard for the open clusters and things like that. It should be fine. Veil at the end is going to be way too big for it. So even though that's one of my favorite objects, probably won't get that one tonight because it'll be just way too big. But anyway, we'll see what we get to. So that is the setup for tonight, using the C8 at about f4.2. And so why don't we get started here. Let's see, the first object is, I did not make a list to go through. I did not make an observation list in Stellarium to go through here, and so because we're going to kind of do this in the order of his list, regardless of the order of the sky. So we'll just have to be flopping around the sky and seeing where we end up. So NGC 281, the Pac-Man Nebula, is our first nebula. So let's just NGC 281, doink. And that's going to be right there, just under Cassiopeia. So we're going to have to meridian flip to get that. It's actually a little bit low, but not too bad. So let's zip the scope over there and see if we can start imaging the Pac-Man. Now I'm using a dual band narrowband filter tonight as well. It was another choice I made rather than going no filter at all, which is what I usually do when there's no moon. Tonight I decided to keep the filter in because the objects that we're going to be seeing, most of them will respond well to the NBZ, to a dual band filter. Alright, now let's see where this goes. This kind of went to a wacky spot here, so what I may do is actually just let's see where our field of view is, and let's center on there, and let's see if we see, that's probably it. So let's give it a shot, see where we're at. Sometimes the first slew goes a little wonky. We'll see where we go. So the Pac-Man Nebula is going to be the first nebula we see in these. So this is going to be one of the areas of star formation. And let me get these menus out of the way so we can see. Good evening, Javier. The telescope diameter is 200 millimeters or 8 inches. Hey, good evening, Mike. Thanks for being here. And you see 281. What did... Oh, you know, I should probably reduce this down to... I can't grab it. Reduce this down so you guys can see more of the Stellarium window as well. Come on, grab that. Boy, it's really persnickety about grabbing it just right. Pac-Man, compact emission nebula with embedded protostars. So, definitely an area of star formation. Let's balance our colors. As you can hear, we've got a little bit of a breeze tonight. Well, that is a car driving by, which doesn't happen very often here, but okay. Pac-Man Nebula. It's definitely different operating at f4 versus f1.9. The objects are much dimmer, much dimmer. They take longer to build at f4. It takes that light just a lot longer to get to the camera, and images just take a little bit longer to build. I'm surprised this isn't a bit more red, actually. See what happens as I get more what I may actually want to do is go to a longer sub-exposures. 1 minute may just not be enough. In fact, let's try going to a 3 minute. Let's load this. It'll take longer for the individual subs to land, but I think they're going to be a lot brighter and a lot more colorful. So we may just have to do the waiting. We'll try a 3 minute sub and see how it responds. Right now the histogram peak is very, very close to being off the edge, left edge of the histogram, which means I'm really not getting enough light. And with the slower f4 focal ratio and a much less interesting image. So, prefer not to do that if I can get away with it. Yes, this is the Pac-Man Nebula, NGC 281. I should put that up here, NGC 281, which is, the familiar name is the Pac-Man Nebula. You're very welcome. Feel free to answer any, ask any questions you want. I will be happy to answer them. Can't quite see the time here, so I'm having to kind of guess at the time. I'm guiding with, I have a 60mm guide scope and a camera. And I'm using PhD to guide. Alright, let's see how a 3-minute sub does. Produces way too much blue, so we're going to have to drag that blue down a bunch. Still too much blue, but this is better. Color is definitely a lot better in this one at 1 minute than it was at 3 minutes than it was at 1. So the longer sub exposures are just what we're going to have to deal with tonight, because again the very restrictive filter that I'm using, which helps really pop the nebula forward, it reduces the star sizes a lot, especially with a nebula like this, and pretty much every nebula we're going to look at tonight is in a very dense star field, and so the restrictive filter helps to reduce the stars, reduces them down a lot, which allows the nebula to kind of pop forward. So yeah, so I'm using PhD2 to guide, and so this is my guiding software just kind of running here, making constant corrections to the scope to keep it on the target as precisely as possible, so that we don't get streaky stars and we don't get blurred images. And I should get the music started. So we have that. Telescope diameter, no, it's a fixed diameter telescope. The only thing that you can change is the focal length and the focal ratio, but the diameter of the scope always stays the same. Now let me pull up GC281. It's an emission nebula in the northern constellation Cassiopeia. It's part of the Milky Way's Perseus spiral arm. It's known as the Pac-Man Nebula for its resemblance to the video game character. Edward Emerson Barnard discovered the nebula in August of 1883, describing it as a large, faint nebula, very diffuse. and it has a lot of protostars in it. So it is a place where stars are born, which is why it's on SAY's list. One of the first things we're looking at tonight is this nebula, because this is where stars actually start out. They start out in large clouds of gas and dust that eventually coalesces into lumps, and then these lumps are higher in gravity than everywhere else, so that attracts more gas and makes a bigger lump, which attracts more, which a bigger lump, and it's like a snowball effect, and eventually develops so much mass that the crushing pressures at its core initiates fusion, and a star is born. Exposures are definitely the way to go. We got a little bit of a satellite that went through up here, but didn't go through our object, so we'll leave it. And as I said, tonight we're using the 3.3 reducer, which is an old reducer that was designed to really speed up these Schmidt-Cassegrain telescopes, make them a lot faster optically. One of the penalties that you pay for that is a fairly small field of view, and the stars get a little wonky near the edges and corners, especially when you use a sensor much over half an inch or so in size. And tonight I'm using my 183, which is a 1-inch sensor. So it's expected that the outer edges are going to be a little wonky. The stars have tails on them and whatnot. But the center is actually pretty nicely controlled and still gives me some pleasing images. It actually performs significantly better on this 1-inch sensor than I expected it would. So I'm pretty happy with it. And it gives it's a nice option for my scope, because it gives this 8-inch scope another focal length option by putting different reducers on each end of the scope. I can go everywhere from 400 millimeters at f1.9 up to 2,000 millimeters at f10, and the 3.3 gives me an option around focal length of 800, 850, and the 6.3 reducer I have gives me a focal length of about 1,200. So those are nice midpoints that allow me to use the scope somewhere between the very short 400 millimeters of the focal length of the hyperstar and the 2,000 millimeters of using the scope without a reducer at all. So the really nice thing about these Schmidt-Cassegrain telescopes is how very versatile they are. They're jacks of all trades, not necessarily masters of any of those things. You can get specialized telescopes at any of those focal lengths that will do better than this will, but it does all of them. And it's very, very, very versatile. It's sort of the Swiss Army knife of telescopes, and can do a lot of different things with them. So I've really been enjoying using mine. Really been enjoying it. Alright, let's see if we can do a bit of a color balance here, tweak that a little bit. And maybe tweak this out a little bit. And stretch it a little bit more, see if we can see a little bit more of that nebulosity. About 30 seconds or so. The video I'm looking at is delayed by about 30 seconds or so. So I have to wait to see how my wait a little bit to see how my changes affect the image. Yeah, I think it did pretty well. I think we'll do one more on this and then we'll move on to the next. We're going to be doing a lot of star clusters tonight, open clusters, and I think even one or two globular clusters. Actually, I'm not sure we're doing any globular clusters. I think it's going to be just open clusters, given that we're talking about star formation here tonight. And so those are going to be fairly quick to do. Ray asks why I'm using the optical filter. Not sure what you mean by optical filter. I assume you're meaning the narrowband filter that I'm using. The narrowband filter is really good for nebulae, and so when we're looking at a nebula like this, that's in a very dense star field, it really reduces the stars and allows you to see the nebula much more clearly. If we were looking at the Pac-Man Nebula with no filter, it would be just flooded with stars, and it would be much more difficult to see the nebula itself because of all the stars between us and it. And so the filter really helps cut down all the wavelengths that the stars are emitting, except the wavelength that the nebula is emitting. So in that way, it sort of makes it look like the nebula pops forward, when in reality it's just cutting back 98% of the light from the stars that are essentially blocking it and drowning it out. So that's why I'm using the narrowband filter tonight. So for these nebulae, it's going to work really well. Even for the open clusters, it's going to work pretty well. Because we'll be able to see, the stars will be smaller and less bloated, and we'll be able to see more of the individual stars. No, this is actually a dual pass narrowband. It's letting through oxygen 3 and hydrogen. So it's a dual band, narrowband filter, not a single pass. And the reason for those two bands is because those are mostly what nebulae are comprised of, is hydrogen and oxygen. Hydrogen alpha, hydrogen beta, and oxygen 3 are mostly what they are. So they make filters that allow only those specific frequencies to pass through. And since stars are full spectrum emitters, they emit all spectrums of light, it basically allows the nebula's light to come through unaffected, but knocks back about 98% of the star's light, which makes them much smaller, more muted, and allows us to see the nebula through them. Alright, so there is the Pac-Man. So let's see what, let's go to the Wizard. 7380. NGC 7380. Wizard, aka Golden Snitch. Yeah, we're right next to her. Good. Alright. There's the Pac-Man. So now let's move on to the Wizard. Slide the scope on over there. catch up here. There we are. Alright. Now let's plate solve on that, make sure we're right on it, and we pretty much are. Alright, so start imaging. Okay, and this is 7380. Well, that's building. Okay, it's a young open cluster of stars. Cepheus, discovered by Caroline Herschel in 1787. The surrounding emission nebulosity is known colloquially as the Wizard Nebula. William Herschel included his sister's discovery in his catalog. It is extremely difficult to observe visually, usually requiring very dark skies and an oxygen-3 filter, which is one of the bands that is allowed to pass through the dual band filter that I'm using. So there it is, just really faintly up there. I'll put a really noisy preview image up here. What it's going to look like, and when we get the actual first 3-minute sub in, it'll look a lot better than that. But it's the cluster, the star cluster itself is about 20 light years across. Age range estimates are from 4 to 12 million years, which is obviously a very young group of stars. The center of the cluster lies DH Cephei, a close double-lined spectroscopic binary consisting of two massive O-type stars. This pair are the primary ionizing source for the surrounding nebula. So those two stars are actually illuminating all of it. Let's see if it's the annotation will tell us which ones those are. So it's just generally giving us this, and then the Sharpless 2-142 object is the nebula itself. I don't know that we're gonna. I don't know that the. Yeah, I don't think the annotation is going to. Well, I shouldn't be zooming in when the image is this crappy right now, anyway. Hey Ronald, I've been well. How about yourself? We'll let a few subs come in here first, and then we'll. Well, right now it's very noisy because I have it stretched really hard, and the reason I did that is because see, I have it just stretched really hard on the histogram. Once I get the first image here, which is going to land in just a few seconds, I'll be able to do a stretch that's much less noisy. Basically, I'm using a profile that has all the settings for a 3-minute exposure, but only doing 1 minute of exposure because laggy. Alright, that didn't do what it was supposed to do. Wow. These colors are completely wackadoodle. Huh. I don't know why that's doing that crazy stuff. Anyway, I'm using a profile that allows for a 3-minute sub-exposure, but only doing a 1-minute initial sub-exposure in order to just have something on the screen while we wait for the first 3-minute exposure. See, this one has a lot less noise. You can see this is pretty neat looking nebula. Actually, a lot of billowing, sharp cloudiness to it. Well, yeah, I'm glad to be here tonight, Ron. It's it has been a minute. When I went to put together the announcement for today's broadcast, it looked like the last one I did was almost 3 months ago. And I thought, 3 months? Really? Have I not been on in that long? But I thought I had been on since then. Apparently, July and August, I never got on once. So, there you are. Okay, and this one, 7380, I can put that up here. 1, 2, 3, 7380. Got that. And, also, Ray, to answer your question further about the noise in the first exposure. Yes, it was noisy because it was so short in this case, but the first sub-exposure always is noisy, and it's subsequent sub-exposures that really help reduce the noise and increase the contrast. So the first one's almost always noisy. First one's the worst one, but the image just keeps getting better and better as you go along. Is what we're doing. Let's see, anything else interesting about this? I don't think. So again, it's at the center of the cluster lies a very close pair of O-type stars, and they're the primary ionizing. They basically illuminate, ionize the nebula itself. And they're driving out the surrounding gas and dust while triggering star formation in the neighboring region. So there are at least 14 pre-main sequence stars and 17 main sequence stars that are pretty young. So again, the reason Say put this on our list was because these are the kind of things that are producing brand new baby stars. This is a stellar nursery. This is where they get their start. How's the weather where I have the telescope set up? Well, it's pretty nice tonight. Clear, dry. Got a little bit of a breeze right now. It crops up and then dies off, so not perfectly ideal, but other than that, pretty nice. It's probably 85 or so, I'm guessing. Let's see what the thermometer says here. Yeah, it's probably about 85 at the moment. We've been temperatures just above 100 during the day, which for September is pretty nice. So, pretty nice conditions for astronomy. Ray asks, extreme contrast, losing details. The The other downside of the delay I experience between doing something and having it show up on the screen that's monitoring the broadcast is oftentimes people ask me questions to things I said a minute ago, and I don't remember what I said a minute ago. So I'm not sure, Ray, what your questions mean about extreme contrast and losing details. Not sure where you're going there. So if you can clarify those questions, I can hopefully answer them for you. I'm also realizing that my microphone was a little bit further away from my mouth than it should have been. So hopefully you can all still, you can hear me a bit better now. Try to keep the microphone pretty close to my mouth, especially when it's a breezy night, because it you just catch a lot of wind noise in the mic. Does the extreme contrast of the filter and processing make for loss of detail? Not really. The detail is really in the nebula itself, and the filter is allowing the particular spectrum of light that the nebula is made of to pass through. So pretty much the nebula passes through freely, and the stars are just tapered way back. So you don't lose a whole lot of detail in the nebula itself by using the filter. You might lose a tiny bit, but you gain way more than you lose. Again, if we were not using any filter at all, this nebula would be really hard to see, given the flood of stars that would be in front of it. The stars that we see in front of it right now are very greatly reduced from what we would see with no filter at all. So we're actually seeing a lot more detail in the nebula right now than we would if there was no filter. So hopefully that answers your question. And again, that's way too much blue. Likes throwing in too much blue. And thank you for clarifying the question. The blue, Ray, is just coming from the histogram not being adjusted properly. So once I adjusted the histogram properly, all that blue came out. When you balance the colors in the histogram, it kind of makes an approximation, which usually is pretty good. Basically, it tries to align all the peaks of the colors, red, blue, green, and the white luminescence channel. Sometimes, for whatever reason, it's off by a bit. Certain filters will drive it, sometimes a little batty. The NBZ is famous for making it produce too much blue. Okay, Ali, I'll see you after the game. Enjoy. We're gonna finish up on the wizard here, and then we're gonna go to see some. Now we're gonna move from the places where they are born, the nebula in which they are born, and we're gonna actually see some. The next phase is the clusters like this consume most, if not all, of the gases, and then all that's left is sort of a cluster of stars that then kind of moves out on its own. And so next we're going to see some open clusters that are some fairly young stars that are kind of the next step, the next phase. Deep sky blue. Raleigh scattering from particles much smaller than visible light. Well, sounds like you know a lot more about it than I do. Alright, we'll take one more sub here. I'll probably stretch this a little bit more. We'll get that last sub in and move on to some open clusters now. For that, I'm actually going to change back to 1 minute subs, because you definitely do not need very much time on star clusters. They're very bright objects, unlike these nebulae that are much more faint objects and need the extra exposure time to see them well. But the Wizard Nebula, I'm not sure why they call it the Wizard Nebula, where the wizard actually is in here. But okay, our last object for the birth of the stellar nurseries. So now we're going to go to NGC 869. NGC 869. What just happened? Why didn't you go? There we are. Which is the double cluster. Part of the double cluster, anyway. With this reducer in, my field of view is so small that I can only see one lump of the double cluster. But we're going to go to it. Okay, and let's zip over there. It's a lot lower in the sky, but again, it's kind of such a bright object. It's right next to the Heart and Soul Nebulae, which are some pretty cool things to see, except my field of view is too small. Okay, so you are now there. Let's get U plate solved. Yeah, you can see star cluster right there. Probably just going to pull it down a little bit. Yep, right there into the view. And now I'm going to want to reduce this to the 1 minute. We'll go down to 1 minute here. Because we are not going to need more than 1 minute, even with the filter. We're not going to need a whole lot of time to see these clusters. They're very bright. Even 1 minute will probably be a bit much. 869. It's about 7,500 light. These clusters are about 7,500 light years away. It's about 14 million years old. The double cluster is a really nice binocular object. If you get out there with your binoculars, yeah, you know what? I should have left that alone. Oh well. If you get out there with your binoculars, these are really fun objects to see. So this is one of the two. There's actually two here, one here, and one here. But we're only actually able to see kind of one in the view. The other one is just off the screen to the top here. But this is a very young cluster of stars, only about 14 million years old. Let's see, anything else interesting here? The clusters are both located in Perseus, a few hundred light years apart from each other. The clusters are first recorded by Hipparchus, thus having been known since antiquity. Yeah, thousands of years we've known about these, the double cluster. It's often observed with small telescopes and photographed. As like I said, it's a great binocular target. And it's right between Perseus and Cassiopeia in the northeast sky. So it's a great target for small telescopes and binocs. It's in the winter Milky Way, but it's visible even right now. Mostly bright blue stars, very young stars. Try cranking up the luminosity a little. Probably should have left the adjustments alone that I had before. One of the challenges of the histogram peak being jammed so far over here to the left is there's not a lot of room for color adjustment. But Ray asks, is the 183 a good match for these optics? Yes, it is, because of the very small pixel size. Well, actually, with the hyperstar at about 400 millimeters, it's a good match. I'm a little oversampled at 850 millimeters where I am. It's a little bit oversampled, but not badly. When I'm using the 6.3 reducer and I'm at about 1200 millimeters, I bin to the sensor, the 183, and that works out about perfect. So, yeah, the 183 is actually nice. Even at f6, you can bin it, and it will get you a good image scale. With the hyperstar, it gets a nice image scale. This is sort of in the middle, so it's a little bit oversampled, but not bad. If I was using this at the full 2000 millimeters of focal length, yeah, I'd want a camera with bigger pixels. But 183 is pretty versatile. I suppose I could even bin 3 or bin 4 it if I was going to use bin it even harder if I was going to go to the full focal length. But yeah, I mean, I have yet to find a better camera that works overall better with this setup. And I've tried a few, including a 585 most recently, and 183 still beat it. So, Javier, this is one of the clusters of the double cluster. It's called the double cluster, which is two little clusters of stars that are about 400 light years apart, and they exist between the lazy W of Cassiopeia and the constellation Perseus. They're kind of right in the middle. And you can actually see them naked eye if you have some fairly dark skies. But this is one of the two clusters, NGC 869. 869. Should have put that up there before. So these stars are about 14 million years old. We've done about 6 minutes on that. So we can actually, because it's fairly quick to see, we can actually just zip over and see the other one. Try to leave them both in there. Unfortunately, the camera is not ideally situated to see. I just don't have quite the field of view to see them both. But we'll get one at a time. But with a small telescope, or like I said, binoculars, it's a great little target to look at. Great little target to look at. And what do we got next? After 869, we got M39. M39. Okay, we're going to go up sky a little bit. Good. Okay. Should have our other half of the double cluster coming in here momentarily. Again, a nice collection of young stars. See, this one's got a bit more of a mixture of the orange and the bluer stars. Definitely got some reddish orange ones in here and some yellower ones and some of the younger blue ones. So the other half of the double cluster, or NGC 869. Actually, do each one of them? I think they actually might even have different NGC numbers, one for each of them. But in any event, like I said, they're pretty easy to find with a telescope or binoculars. Right between Perseus, below Cassiopeia and above Perseus, right, kind of right between them. In the band of the Milky Way, there's these two brighter spots of clumps of stars that show up. Okay, M39. Definitely got more star color variation on this one than on the upper part of the double cluster. I guess the lower part because we're upside down. Okay, so M39 is going to be next. Another open cluster of stars. So let's go up sky to that one. Solve that. Got pretty close. This one's going to be, this cluster is almost going to be the size of our field of view here. So much more of an open, scattered cluster. 7092. Or Messier 39. It's an open cluster in Cygnus, sometimes referred to as the pyramid cluster. It's 2 degrees south of Pi Cygni. The cluster was discovered by Guillaume Le Gentil in 1749, and then Charles Messier added it to his catalog in 1764. When observed in a small telescope at low power, the cluster shows around 24 members, but it is best observed with binoculars. It has a total integrated magnitude of 4.6. It's about the size of the full moon. It's about 1,000 light years away. So you can see it's sort of a scattered collection of stars. This is a much looser, more open cluster than what we've been looking at so far. What did Say talk about it? It's around 270 million years old, loose nearby cluster of bright stars with brightest members close to leaving the main sequence. So they're kind of spreading out. So again, as the stars are born in nebulae, in clusters, because all the gas is in one place, so all the stars kind of cluster together, and then they consume all the nebulosity. Ow! Sorry about that. They consume all the nebulosity, all the gases, and then slowly over time they disband and disperse, sort of go away and become more and more open and loose clusters. So that's kind of what we're seeing from the double cluster, where they were more tightly close together. At about 14 or 15 million years old, these are now close to 300 million years old, and so they're more mature and they're spreading out more and kind of heading in their own directions. They want to make their own lives, so to speak. So a much more open and dispersed cluster. And again, a nice binocular target to look at. Open clusters are really good for that. 61 Cygni. Yeah, I didn't think. Yeah. Well, actually there is. Custom object. Yeah, it's a double star. Well, let's see if we can pick it out. Double star with annual high proper motion. Alright, let's go see what 61 Cygni looks like. Not very far away. See, here's the North American nebula that he wanted us to start out with, but there's the size of my field of view, and there's the North American nebula. That's why I didn't bother going over there to look at it. I mean, I guess we could go over and look at a part or piece of it, but it's way too big for my field of view. Okay, well, there looks like the double star right there, so let's just start imaging. What did he say about it? No, it's a double star. Well, you can actually see the motion of the two stars relative to each other. So if you come back and image it every once in a while, you can see the motion with each other, their relative motions. Yeah, boy, no mystery as to where those are, huh? A double star, there they are, very close together, and so if you come back and look at them over time, they move with respect to each other. So, cool. Oh, thanks to whoever gave me the thumbs up. I just noticed there's a few thumbs ups there. Thank you for the thumbs up. Much appreciated. Kind of cool looking double stars. Okay, so now we're going to go to hydrogen runs out. These are sort of what we've been looking at right now is sort of young, but stars entering sort of their main sequence, main lifetimes of the stars. So now we're going to get to as they get a bit older. This next cluster is going to be 8 billion years old. It has a whole bunch of red giants. The hydrogen runs out, the core contracts, and the envelope swells and cools, and the star turns red in color. But this is a pretty cool looking double star. Let's go look at a cluster of red giants. 6791. Oh, we're flipping over to the other side of the meridian. Alright. Meridian flip. Alright, here comes the scope. Somewhere about there. And let's plate solve in on that. All right. Again, 1 minute should be enough. Okay, so this is going to be NGC 6791. Which is going to be an open cluster about 8 billion years old. Has a lot of red giants. It looks like a glob. Probably going to be pretty red in color. Guess we'll find out. Yeah, it's a dense little spot. Yeah, these stars are looking kind of squidgy, so I'm wondering if I need to check my focus. And I'm in a very convenient spot to do that right now because right near Vega, which is a nice bright star. Oop! That's not what I meant to do, but whatever. So a nice bright star. So I think that's what I'm going to do right now. We're going to take a little bit of a time out here. Stars are looking a little weird. So I'm going to go. We're going to pop down to Vega real quick and put the Batinov mask on and check the focus of the scope because I think it probably needs to be adjusted, tweaked a little bit, because this cluster is a lot of fine little stars, and I like to see them as clearly as possible. So I'm gonna go do the focus. Be right back. Okay, it was definitely off a little bit, but that should be off. That should be a lot better. Okay, let's go back to where was I at? 679. Well, it'll be in the memory. Go back. Go back. Go back. And you go back. Good, you're right on. Alright, I think we'll get a much sharper image this time. There we go, a nice cluster of stars there. Give this a few more subs to Let the noise clear out. Are these standard sequences or produced for tonight? I assume you mean the sequences that I'm using in SharpCap to make the camera settings when I go to either look for a new object or to settle on an image and object. And yeah, the settings, the sequences that I'm using here are pretty much the ones I use all the time. They're specific to camera. You see I still have a couple from the 585 in here, even though I don't have the camera anymore. And so these are based on the gain settings that I'm going to use. I use the 183 either at what's considered full unity of gain 111 or half unity gain of 53. And so those are just really the two gain levels that I use with the camera. And so when I'm starting imaging, when I've settled on an object and plate salt and centered it, I'll pick one of these to either one gain of 111 or a gain of 53. And then when I'm done imaging the object and I want to move to it, then the next target sequences set the camera for maximum gain and much shorter, 1 second exposure and stuff, so that when I slew to the object, I can find it and plate solve on it much easier. Whereas the imaging ones obviously are once I'm settled on the object and I've plate solved and centered it, then I can start imaging at whatever my desired gain levels are for the particular object that I'm shooting. So hopefully that answers your question. But let me know, Ray, if it doesn't. But this object is about 8 billion years old, has a lot of red giants in it. Let's see if the annotation, it doesn't really say much about it. Just that there it is. But it's a much older cluster. Did he say it? It looks like a glob. I wonder if it could have been a glob. It's such an old, with such an old cluster, that it hasn't dispersed more. I wonder how far away it is. 6791. Let's see if Wikipedia tells us. 6791. Open cluster. Discovered by Friedrich August Theodor Winicke in 1853. Roughly 8 billion years old, and with an iron to hydrogen abundance ratio that is more than twice that of the Sun. It's one of the oldest and most metal-rich clusters in the Milky Way. It's contrary to the typical rule of thumb, where older means more metal poor. It has an unusually high population of stars, and is among the most studied clusters in the sky. Among the dimmest stars in the cluster are groups of white dwarfs that are 6 billion years old, and another group that appears to be 4 billion. The ages are out of sync with those of the cluster's normal stars, which are 8 billion years old. This seeming contradiction in age for this cluster has been studied, and a solution proposed with age of about 8 billion years. Well, it's an older cluster, which is why Say put it on the list. Lots of red giants, apparently. Definitely a much dimmer cluster than what we've been seeing. This one might be a harder target with binoculars, but still it's a fairly decent size, so I don't know. Binocs might be able to pick it out. Give this one a couple extra minutes, more so than the others we've done, because it's just a fainter object. While it's doing that, what do we have? 70, 79. Oh, Caroline's Rose. Yeah. Caroline's Rose cluster. Oh, back over on the other side of the meridian again. This one will be a bigger, brighter cluster. Finish this sub and head over there. Flip back over the meridian again. Alright, there's 6791. Now let's go look at Caroline's Rose. It's going to just about fill my field of view. Put me right there. Not bad. Okay. Ray says, magnitude of an open cluster is determined by its integrated magnitude, which is the total brightness of all the individual stars in the cluster, or by the apparent magnitude of its brightest stars. Good to know. Okay, 789 or Caroline's Rose. Get an example. What does it say about it? Significant number of red giants. It's about only 1.6 billion years old. Cool. I think I want to go. It's actually cooling off a little bit out here, so I think I want to go get another layer on. So while this image builds, I'm going to run in and get a layer on. So I'll be back. Ray says it's 55 degrees and 99% humidity here. Imaging S30 and EQ mode. Oh, you're imaging with your C-Star 30. Cool. What are you imaging? Well, Caroline's Rose is coming along pretty nicely here. Yeah, looks about right. All looks pretty good. M31 streaming on Discord. Okay. Old Andromeda's galaxy. You look like you need to be restarted. Should not be having difficulty. Guiding is going wackadoodle. Oh well. Well, we need to be on this more than another minute or two anyway. Caroline's Rose. This is also another great binocular target. A nice thing to see. In the binocs. Right above Cassiopeia. Double clusters below. Caroline's Rose is above. And then Ray is over here on the Andromeda Galaxy. A great binocular target. Triangulum Galaxy down here is a great binocular target. Some nice stuff coming up for the fall. Caroline's Rose. Okay, what are we doing next? The Crescent. Ah, one of my favorites. Especially with this setup. This setup does it pretty well. Crescent Nebula. Yep. Oh, guess what? We get to hop the meridian again. Is it just on the east side? Yeah, it's just on the east side. Drat. Okay, well, back across again. Alright. Keep flipping back and forth and back and forth and back and forth. There's a pretty good breeze. Kicking up out of nowhere. Alright. Oh, it's getting better. Okay. Alright, now for this, I'm going to want to do 3 minutes again. This one's definitely going to need the 3-minute treatment. Okay, and now go. So again, even though I'm setting up for 3-minute exposures, our first sub-exposure will only be 60 seconds, just so we have something quick and dirty on the screen while we wait for the first 3-minute sub. So it'll be a bit noisy. Yeah, Mark does good work. He's been playing around a lot with his smaller setups too. He had a Dwarf for a while, then a Sea Star for a while, and now he's got another setup, highly portable setup that he's been playing with. Where is the crescent? Okay, I'd say we've got it pretty well dialed in. Let's go to 3 minutes. This is a pretty nice object. It's about perfect for the for my particular setup. Anyway, while we are waiting for that first 3-minute sub, I mentioned nebula created by the powerful stellar wind from a massive Wolf-Rayet star, which is an evolved, very hot and luminous star that has shed its outer layers. So, let's see what else. What else Wikipedia has to say for it? It's an emission nebula in Cygnus, about 5,000 light years away, discovered by William Herschel, 1792. It's formed by the fast stellar wind from the Wolf-Rayet star WR-136, colliding with and energizing the slower moving wind ejected by the star when it became a red giant around 250,000 to 400,000 years ago. The result of the collision is a shell and 2 shock waves, one moving outward and one moving inward. The inward moving shock wave heats the stellar wind to X-ray emitting temperatures. It's formed by the fast stellar wind from the Wolf-Rayet star colliding with and energizing the slower moving wind ejected by the star when it became a red giant. So earlier, it ejected a bunch of its material 200,000 or 300,000 years ago, and then more recently has been pushing a much more intense, faster wind that then creates all kinds of shock waves because it's colliding with the older stuff. Thanks, Ray. Thanks for being here. I appreciate it. And have a great evening. I'll see you next time. Alright, let's clear that out. Now we'll get our first real image of this, which is a pretty cool object to see. Let's see how we do there. Yeah, that's not too bad for the first sub. Alright, what else we got here? While this object is considered bright by astronomical imaging standards, visual aid is relatively faint. For most telescopes, it requires a ultra-high contrast or oxygen 3 filter to see it. That's one of the reasons we're seeing it tonight, is that this is another one of those nebulae where my dual band filter really helps because it's blocking a lot of the star field. If you can see, let's look at it in the Stellarium. So you can see the band of the Milky Way goes right through here. And so there are lots of really dense, so this is in a very dense star field that without the filter that I've got in here, this would be hard to see through all the stars. But again, this filter cuts back 98% of the light of those stars, and so it allows the nebula to be seen much better. And so what they're saying is, even if, if you're going to use a telescope to look at this, getting an oxygen 3 filter is very helpful for the same reason. It really cuts back on all the stars in the star field it's showing up in, and allows the nebula to be seen a lot better. Under favorable circumstances, a telescope as small as 8 centimeters with a filter can see its nebulosity. Larger telescopes, 20 centimeters or more, reveal the crescent or a Eurosine shape, which makes some call it the Eurosine Nebula. Yeah, I guess I kind of see that, huh? The Euro symbol on its side. Kind of facing downwards. So we got a couple of planetaries showing up here next. These are going to be really, really small. So we'll have to see how well we can do with those. Then we've got the Helix and Saturn. Saturn again is a very small planetary nebula. And the Veil Nebula is huge. So, some contrasts coming up. Very tiny to very large. The Helix is fairly large as well. We'll see how that looks when we get to it, but that may also be too large for my field of view. But maybe not. Maybe not. We'll have to see. Planetaries may be a bit of a challenge, however. They are very small objects, so we'll have to see how well we do with those. Push this stretch a bit more. Cool. Alright. There is the Crescent Nebula. Now 7662. Okay. Again, wrong side. Where is it? Come on. 7662, 6826, 6820, 6826. Ah, good. That's on this side of the meridian, so we'll go with that one next. Okay. Thank you, Crescent. Good job. Alright. On you. Let's go to 6826. Blinking planetary nebula. Oh yeah, there it is right there. Alright, we'll let the plate solving pull it to the middle of the view. And in this case, we're actually going to drop to the 1 minute again. Planetary nebulae are very small, but they're also very bright. Teeny tiny, but bright. So 1 minute should do. I think. It should. We'll correct later if we need to. Alright, yeah, look at that. Beautiful blue planetary nebula. And yeah, 1 minute is definitely going to be enough. In fact, we'll even need to back off on the stretch a bit. I wonder if we're going to be able to see any detail in this. What is 6826? Ow. $68.26. Let's see what 68.26. Planetary nebula in Cygnus. It's commonly referred to as the blinking planetary, although many other nebulae exhibit such blinking. When viewed through a small telescope, the brightness of the central star overwhelms the eye when viewed directly, obscuring the surrounding nebula. However, it can be viewed well using averted vision, which causes it to blink in and out of view as the observer's eye wanders. I don't know that we're going to be able to see. Try really reducing the stretch and see if we can see anything in the center. We can see a slight ovaling of it. See, it's just slightly oval in this direction, but just basically getting a blue ball and not really much in the way of any detail in the middle. If you look at the Hubble images of this, there's an actual eye in the middle of it. Looks like an amoeba with a central core. And it may be that the filter is working against us on this one, I'm not sure. A distinctive feature of this nebula are two bright patches on either side, which are known as fast low ionization emission regions. Yeah, I don't know that we're going to get to see much of any of the detail in this. So I'll just kind of, I might have to be at a higher focal length to really see any detail It's just kind of a blue ball. Yeah, even you can see sort of an ovaling of shape there, but that's all we can really see. Can't see the two bright patches on the edge. Otherwise, it's just a bright blue ball. Not much else to be seen, just a bright blue ball. Maybe another couple subs will help, but I got my doubts. It's definitely looking oval now. It is an oval, slightly oval shape, so it is looking oval. But not much more than that. So they're 1,000 years old. Planetary nebulas are here. Stars with less than 8 solar masses, outer layers are expelled. The hot core ionizes the shell that's being expelled. The planetary nebula phase is brief, lasting only a few thousand to tens of thousands of years. This is what's going to happen to our sun in about 4.5, 5 billion years. Main sequence stars like our sun do this. The hydrogen runs out, and so the core kind of shrinks and contracts, and the outer layers of the stars blow off, and making the star swell up into a red giant. Our star may swell up so big that it actually consumes the orbit of the Earth, so it'll get to be many, many times its original size, and then the outer layers will continue to spread out and dissipate, and leaving a much smaller, dimmer core, but it's not out, so it still irradiates and ionizes the shell of gases that are being expelled, causing this huge globe of glowing gas, and that's what a planetary nebula essentially is. That's why we're seeing this blue ball here. It's a star with a star at the center that's blown off some of its outer layers and is now irradiating, illuminating them. Okay, let's see if the blue snowball looks any different. I doubt it will, but we'll give it a shot. Means another meridian flip. The AM5 is definitely getting a workout tonight, flip-flopping back and forth. Alright, 7662. Go back across the meridian again. another blue ball. This is 7662. Yeah, 7662. It's located in Andromeda. Discovered in October of 1784 by William Herschel. It is described as a magnificent planetary or annular nebula, very bright, pretty small in angular size, round blue, variable nucleus. The object has an apparent visual magnitude of 8.3 and spans an angular size of blah 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 blah. It's about 6,000 light years away. 5,500 to 6,000 light years away. And again, a blue ball. Yep, another blue ball. Another planetary nebula. Central star is a subdwarf O star with 5,250 times the luminosity of the Sun. 5,250 times the luminosity of the Sun. The estimated age of the nebula is 3,000 years. Over 5,000 times the luminosity of the Sun. Huh. Well, we'll take a few subs on this and see if we'll see anything new, but probably not. Saturn Nebula will be another planetary. 7009. Not only a meridian flip, but way on the other, way down south. Well, that's where Helix is too anyway, so Helix will be down here as well. And Helix is 7293. Suppose I could have just searched for Helix. Oh, no, that's on this side of the meridian. Yeah, actually, it looks like it'll fit nicely within my field of view. So we'll do Helix first. We may just blow off Saturn, because it's going to be another blue ball. It's going to be another blue ball. Oval shaped, which is why it's got the name Saturn. I think we'll just go do the Helix. And I don't have to do a meridian flip. In fact, I think we'll just go do the Helix now. This is just going to be another blue ball. So I don't think we're going to get anything more out of it than we got out of the last one. So let's go run down and do the Helix. I'm going to go put the light shroud on since it's pointing kind of right at me. There, that'll make sure that the light from my screens and my headlamp doesn't get into the scope. Okay. For this, I want to go back to 3 minutes. This is going to be a faint nebula again. Load. Okay. And go. Alright, well, we'll see what the first... Let's make sure we are on target here. Yep. Okay, now we'll pull a real 3-minute sub. That's how good it looks with just a crappy sub. So, it should look pretty darn nice with a real sub. Helix Nebula is a planetary nebula, so again, this is a planetary nebula where it's blowing off layers and then igniting, and then ionizing them, illuminating them. It's about 650 light years away, so pretty close to us. It's similar to the Cat's Eye and the Ring Nebula and the Dumbbell Nebula. It's also been called the Eye of God and the Eye of Sauron. For those of you who know the Lord of the Rings trilogy, the Helix Nebula is an example of a planetary nebula formed by an immediate to low mass star like our own Sun, which sheds its outer layers near the end of its evolution. Gases from the star and the surrounding space appear, from Earth's perspective, a helix structure. The remnant central stellar core, known as the central star of the planetary nebula, is destined to become a white dwarf. The observed glow of the central star is so energetic that it causes the previously expelled gases to brightly fluoresce. Its age is estimated to be about 10 to 12,000 years based on the ratio of its size to its measured expansion rate. of 31 kilometers per second. Expansion of the whole planetary nebula structure is estimated to have occurred in the last 6,500 years. Spectroscopically, the outer ring's expansion rate of 40 kilometers per second and about 32 kilometers per second for the inner disk. Okay, well, we better make sure we clear the decks for the first good sub coming in. This is a pretty nice looking nebula for this setup. I wasn't sure. I thought it might have been too large for this setup of mine, but it looks like it's going to do pretty well. Yeah, it looks like it's going to do pretty well. Helix Nebula. Write that up there. And we're actually catching some of the outer ear here as well, which is pretty cool. Don't always get to see that. Some of the outer structure. Just got this one sort of area that kind of blows off a lot further than the rest. Kind of catching it in here too, so that's cool. Yeah. And so the only other one to do after this is Veil, and Veil is a very big nebula, way too big for my field of view. Might be able to do some small parts of it, but it's best done with the Hyperstar, much bigger field of view and much faster, better light collecting. But in the meantime, we get to look at this beautiful thing. I love the blue color in this. One of my favorites. Looks like it ignored the first sub. I mean the second sub. on. Could not align. Boy, why is the FWHM so bad? Boy, these are really bad. Huh. Oh, that stinks. Why did it... Oh, come on. Why did it ignore... We'll optimize for faint stars. See if that doesn't improve things. This is such a pretty object. And we're getting some nice detail showing up in now this outer region, which you can't always get, so this is kind of nice it's showing up. So I'm going to give this a couple more subs, just a bit extra time to have some of this fill in a little bit more. I might even save this image. It's coming out pretty nicely, so I'm going to give it a little extra time. That's pretty cool. I think that came out pretty nice. Might be able to stretch it a little bit more. But I think overall that came out pretty well. I think I want to save that. Darn nice. I'm really liking how I'm getting the outer edge. That outer edge is something you don't always get. So really starting to see some structure in there, which is pretty cool. Actually some decent structure in the cloudiness of the nebula itself too. So very cool. It's quite a beautiful object. I really love the blue in this. It's one of the closer planetary nebulae to us, which is why it's so large as compared to most of them, which are just these tiny little bright blue or green balls. This one is pretty close to us, so it's pretty big. So this is one of my favorites. I like being able to see this. Just gotta make sure, yeah, I'm not near the meridian yet, but getting close. And now what we're going to do next is we're going to go across. The last thing on the list is Veil, which is down here, I believe. Yes, the whole Veil complex. And the problem with Veil is it's just so big. It's just so big I can only do it sort of in chunks. But kind of do that. Maybe that'll be our next target. Anyway, while I was wasting time there, I snuck in another sub. So, we got 8. Yay. In fact, I might stretch it. Well, actually, let's stretch it a little bit more. Save it again. Yes. Overwrite it with the higher stretch. Pretty cool. I like that I got this extra structure in here. That's a pretty cool image. Alright, let's go see what we can get for Veil. Veil is also a very beautiful image. It's a beautiful object. Just the biggest downside is that it's too big for my field of view. And again, because I'm using the 3.3 reducer, because the object does span the whole field of view, when it gets near the edges it gets pretty muddy. So you really, with an object that's bigger than my field of view, when using this reducer, when you get to it really sees limitations. And when it gets out here, it's going to be pretty mushy. But only 0.14 degrees, not bad. Oh, hey Mike, did you catch the end of my helix? You just missed, hopefully you caught the very tail end of the helix I just had up, because I just finished a nice 24-minute integration on that, which came out pretty nice. And we're going to maybe do a couple of chunks of veil. Oh, you did. Good. Glad you got to see a little bit of it. I mean, I could pull up the image. I did save it, so I could pull up the image if needed to. Wow. Guiding is going absolutely bonkers. As it sometimes does. Yeah, there we go. We got some of it. Okay, well, let's see if the guiding is coming back. The deck axis is just completely gone. And it continues to leave, so... Oh, now it's finally coming back. Okay. I'd like the guiding to be somewhat reasonable before I actually start saving it. Yeah, it looks like it's pretty good. Okay, let's go to 3-minute subs now and get an actual start on our good subs. The guiding has become caught up on whatever slop or backlash it had going on, which isn't supposed to exist in harmonic mounts, but there you are. Alright, well there's the first throwaway 1-minute sub. Just giving a little taste of what we're going to see. But again, because I'm using a 3-3 reducer, the middle parts will be somewhat sharp and the outer parts will be somewhat mushy. So, one of the limitations of using a 3-3 reducer. But I've actually been quite pleased with the performance I've got from it. It has performed much better than I expected. So, I'm pretty happy with it. I think I'm going to keep it. At least it gives me another option. I like having the option of 800 or 850 millimeters of focal length, because I already have the 400 millimeters with the Hyperstar, and I have the 1200 millimeters with the 6.3 reducer, and I have the 2000 millimeters with the full, the native focal length. So having something between the f2 and the f6 is it's nice to have. If by some miracle someday a night owl shows up, well, maybe I'll replace the 3.3 reducer with that, but until then, this'll work. Okay, let's get this Throwaway sub thrown away. Get ready for the first good one. It's probably going to be about right. Something like that. This is going to be Eastvale. A pretty little thing, to say the least. Much better with the Hyperstar. I can see a much bigger chunk of it. It's a lot brighter at f1.9 than it is at f4.2, but still get more detail this way. Yeah, Mike, this is an NBZ, so it's a 12mm dual band narrowband filter, and it's O3 and hydrogen alpha. I think it might even be a little hydrogen beta in it too, but yeah. Yeah, this is a pretty one. One of my favorite objects over the whole year. It's got some great color in it. The reds and the blues and the greens. When I put the NBZ on the Hyperstar, it's really does a great job with this. I'm going to finish getting this sub here, and I think I'm going to call it a night. So thank you everyone for being here tonight, and thanks for the thumbs ups. It's been great getting those. I see I got quite a few there, so thank you for the thumbs up, love, and I will see you guys next time. Not sure when that'll be yet. I got some nice weather tomorrow night, but I don't think I'm going to be able to make it on for the rest of this week. And the weather's supposed to actually turn sour by supposed to have some showers and stuff maybe by Thursday, Friday, so probably not before the weekend, before I get some nice weather again, but maybe I'll get a chance to come back on before the moon comes back. But in any event, thanks everyone for being here, and thanks Mike, yeah, thanks for chatting at me. I appreciate you being here, and I will see everyone later. Actually, I probably just gotta save this right now, because why not? Just save it. It's worth it. It's a pretty decent image. Again, showing the limitations of the 3.3 reducer on the edges, but still, it came out pretty decent. So, anyway, thanks again, everybody, and I will see you all next time.